All right, I want to go over an example of an externality, a negative externality between two firms. We have a steel firm or steel mill and a laundry business, and the production of steel generates some pollution, and that pollution is going to negatively impact or increase the cost for the laundry business. So starting with the steel firm, we're going to use S to indicate the quantity of steel produced. In its production, it generates pollution. The steel mill operates within a market of other steel firms, and so we're going to have this firm as a price taker in terms of steel production, and its total profit, of course, is total revenue minus total cost. The laundry business, in turn, is producing L. The total cost of cleaning the fabric is an increasing function, okay, of the amount of clothing it's cleaning, and this is the important part, the emissions from the steel mill. This is the external part. All right, this is the unaccounted for cost due to the pollution. The laundry firm also operates in a market with other laundry firms, and it's choosing its inputs into production to maximize its own profits. The functions we have, caught an error there. I should say total revenue. But anyway, we have the total cost. The total cost is simply S squared. We're using simple functional forms here. And that's the cost to the steel firm. The cost to the laundry business is the square of its quantity produced, and then it has this interaction term, and this is that external cost. So that's where it shows up in our numeric example. Okay, the overarching point here is that we're going to illustrate that with two profit maximizing firms, we're going to get a profit level. We can add those together, and that could be kind of our social profit level, our measure of welfare for these two firms. Then we could show that we can do better, right? When we internalize these external costs, at least socially, we could do better. And we'll illustrate that. The revenue is simply the price of the two goods at the unit level, price of steel, price of laundry. These firms are price takers. So we're going to give these exogenously. The price of steel is $8, right? So that P of S is 8. And laundry 10. We'll first look at the market equilibrium. So we'll assume that firms try to maximize profits. What is the profit maximizing condition for the firms? Well, profit is total revenue minus total cost. All right, and if we look at the profit for steel, we would have total revenue steel minus total cost, which is, if I recall, $8 times S, right? That's total revenue minus S squared. So that's our profit function. Now, to find the maximum, we're finding the change in the profit caused by a change in steel. Right, and we're going to set that to 0 because that's where profits are going to be exhausted. Or in other words, if we look at this, 8, which is the marginal revenue, minus 2S, which is the marginal cost, equals 0. And so that profit maximizing condition is the well-known marginal revenue equals marginal cost. All right, so already we can see for the steel firm, this is going to be a simple bit of algebra there. And let's make sure we have both firms as we move on. I've already kind of derived this. 2S was that marginal cost for the steel firm. The marginal cost for the laundry firm is a little different. It's 2L, but it's also plus S. And that's, again, at the margin, finding that external cost at the margin. All right, and that's for the laundry. Now we know the profit maximizing condition. We can actually see pretty quickly what steel level is. It's 4, but we'll formalize that in a minute. Let's find those quantities and profits for each firm so we can be formal about it. So for the steel business, which we just went over, I don't know why I keep going in between business and firm or whatever. It was marginal revenue equals its marginal cost, 2S, sorry. So S, and we'll call this the unregulated market outcome, would be 4 units. All right, so M for kind of an unregulated market outcome. And in terms of the laundry business, it has its own profit, which was the price of laundry times the quantity, minus the total cost, which was L squared plus L times S. All right, and if we look at the change in the profit for the laundry caused by a change in the thing that they can control, right, L, or choice of L, well, we get the marginal revenue, which is price, minus, that's a parenthetical statement, 2L plus S. All right, and that, of course, is set to 0 to find where profits are exhausted. So we have 10 equals 2L plus S, 10 equals 2L plus 4, right? Which is 6 equals 2L, and L market is 3. So at this point, we've got the production value, and now we got to find the profits for these firms. So we're going to plug in 4 and 3 into their profit functions and calculate these accordingly. It shouldn't be too difficult. The steel firm, and we'll say at a steel level of SM, which is 4, is the price of $8 times the 4 units, whatever, metric tons, whatever it is that they produce, minus the cost, which is S squared. And if you do this little bit of arithmetic, we get $16. The laundry, which depends on SM and LM, actually both of them, would be 10 times 3 units minus 3 squared plus 3 times 4, right? The 4 is the units of steel. And again, a little bit of simplification, and we're going to get the joint profits based on these two values is 25. That's going to be important. I mean, not for the point estimate, it's arbitrary, but the relative estimate is we're going to show that 25 is less than what would be socially optimal for joint profits. And so when we address this externality, when we internalize the externality, we can do better as a society. In this case, our society is simply 2 firms. Let's look at it. So the efficient level of steel and laundry production. Efficiency, right, is maximizing net benefits. In this case, it's profits, right? We've just simplified everything. That it's just profits, right? So maximizing the profits of both firms. So we've got our joint profits, and we're going to choose L and S to maximize the joint profit function, right? So if I was going to expand on this, it would look like this. S and L. The total revenue would be $8 times the quantity of steel plus $10 times the quantity of laundry. Right? That's the total revenue of the joint two firms. And then the cost is, well, the steel had that cost, if you remember, S squared. The laundry had their L squared, and then the interactive component, or the interaction. And this was total cost. Both. So that's what it looks like. We got to maximize that bad Larry. Okay? And this is, I don't know, I'm just kind of typing it out here. We want to find, at the efficient solution, what's the quantity produced and what are the profits, and then compare those profits to the unregulated market, the $25 we just kind of isolated. All right, so we want to maximize by choosing steel and laundry the following function. It's S and L. Right? Sometimes I flip L and S there. Doesn't really matter. And let's do steel first. So I'm taking this function, and I'm saying, all right, I got to find the change in this function caused by a change in steel. I'm going to set that equal to 0. I'm using just the, whatever this is, the power rule in calculus, just the first derivative here. 8 minus 2s plus L, and that's equal to 0. All right? And we could organize that and say, okay, well, whatever S square star, and star is efficient or optimal, is going to look like this. I'm just reorganizing, right? 8 equals the L minus 2s, and then I can find S star. So S star is a function of L. Of course, X star is going down as L goes up. And we'll see that the flip side of that is also true. How does this profit function change when I increase L? Marginal revenue of 10 minus, again, 2L and plus S. So S is now showing up in both because it matters, right? It didn't matter for the individual steel firm trying to maximize his or her own profits or its own profits, but for a social planner, we have our policy hats on, it does matter. So L star, similarly, looks like this. Okay? And we know, okay, if we pop in this expression into L up here, and then solve for S, we'll be able to get our analytical solution, right? So in other words, once I did that, it would be S star equals 8. Well, I'll just remind us of what this was, right? This was the thing. And now if I just take the expression for L and I pop it right in there, you can do this any number of ways. You can do this any number of ways. Right? 2 as my denominator there. Okay, which is going to, if we just want to simplify this out for a second, and then we would get 4, and I should be explicit. This is now S, that's the same value. S star 16 minus 10 minus S. All right. And if you do this, right, we've got, well, let's just go for it. Oops, this is S. We have 3S star equals 6, S star equals 2. All right, so our efficient level of steel, this is the efficient quantity of steel, is less than the profit maximizing individual of 4. So whatever those units are, millions of tons, have gone from 4 to 2, has been cut in half. All right, and then to figure out laundry, if you go back here, L star is 10 minus S over 2. All right, so we've got L star equals 10 minus S over 2. L star equals 10 minus 2 over 2. L star equals 4. All right, so we've got an increase in laundry production in the efficient solution and a decrease in steel. And let's look at how this affects profits. All right, finally, we'll say, okay, S star was 2 to remind you, L star equals 4. The profit level for the steel firm with S star is 8. Price of 8 times quantity of 2 minus 2 squared. That's 12. Okay, so the steel firm has reduced its profit from 16 to 12. And the laundry, which it depended on both, if you recall, was 10 times the 4 units that they produced. Now it was 4 squared, and the other cost was 4 times 2 now. And that is 16. So the laundry went from 9 to 16, so it's up 7, right? And steel's down 4. So you can see there's a potential Pareto improvement. There's passes the Caldor-Hicks, where the winners win more than the losers lose. The winners could compensate the losers. And we say, okay, well, let's add these S plus L and at the efficient solution, and this is $28 or millions of dollars or billions of dollars. So 28 is greater than 25, and so the point is that the efficient level of production is different in the individual optimal level of production is different, right? The steel, the polluting firm, goes down. Laundry, the recipient of that pollution, would go up in an efficient solution, right? And for society's up, the $3 $3 million, $3 billion, the difference between 25 and 28. This is the goal, right? This is what you capture from internalizing that environmental externality. All right, and where we go next is how do we get there? Do we rely on like a Coasian bargaining scenario where the two entities kind of bargain towards an efficient solution? Or do we rely on some sort of policy like command and control? Do we tax the production of a polluting good like steel? So on and so forth.